We now move on to the modeling and analysis part of this benchmark. Now if you recall from the previous section, we saw that when we increase the number of users from 2000 to 4000, the response time just jumped 40-fold, and a lot of tuning went, a lot of time was spent in tuning, but nothing really helped out. And the audit was coming close by. We were really way off the targets for the response times. And while the audit was around the corner, a lot of time went in finger pointing, whether any configuration file was changed, whether something was changed with respect to the previous benchmark that was causing a problem. And no matter what was tried out, nothing was helping out. Now finally there was just about a day or two left, and whatever we tried out, the result was the same, which was a throughput equal to 48 TPS and average response time for the business transaction equal to 40.5 seconds. Now there was only one day left before the auditors would come, and clearly the results were so shabby that we would get disqualified. So essentially, in all this confusion, with just about a day left, somehow it triggered that why don't we build a very quick model, and that is where the experience of simple modeling helps. If you recall, we had done our first test with z equal to 3, and there we had found that even with 500 users, the average response time exceeded the target and reached 7 seconds. But what was also important was that in that test, the throughput saturated to 48 per second. When we ran with 2000 users and think time was 39 seconds, the average response time was within SLA. It was 1.1 second for the entire business transaction, but the throughput was actually saturated at 48 per second. That is business transactions per second. And now when we went to a double number of users of 4000 with the same think time of 39 seconds, our response time jumped 40-fold, but the throughput was still the same at the saturated level of 48 per second. Now this clearly shows that the throughput has reached this limit, and therefore there is some bottleneck that is limiting the throughput. Now if you recall our first video in this section, in this presentation on elementary performance modeling, the theory part of it, there was a bottleneck law which said that the throughput would be 1 over Dmax when the bottleneck is hit, where Dmax is the maximum average demand at any component or any resource in the system. So if we have throughput saturating to 48 per second, wherever it is at the bottleneck resource, the maximum demand is 1 over 48 or 20 milliseconds. Now if you recall Little's law, which says that n is equal to x times r plus z, where n is the number of users, x is the throughput, r is the average response time, and z is the think time plus interiteration time. Therefore we can easily convert this to get an equation for r equal to n over x minus z. Now in addition to this, if we say that at saturation time the throughput x is equal to 1 over Dmax, we can plug this in for x, and therefore we will get that at saturation the average response time r is equal to n Dmax minus z. I mean, in normal cases this will be a lower bound for r, but at saturation it becomes an equality. Now if we really try to apply this simple model and say that if r is equal to n Dmax minus z at saturation, Dmax is 20 milliseconds. Now we have the results in front of us. I'm just trying to show you that even if we did not have these results in front of us, the models would be able to predict the same result. So if we say that n is equal to 500 and z is equal to 3, we apply n Dmax minus z for r. So then r should be 500 times 20 milliseconds minus 3, which works out to 10 minus 3 equal to 7 seconds, which is what we got in the test. Same thing if we apply for n is equal to 2000 users and z is equal to 39, then the average response time r as per our model should be 2000 times 20 milliseconds, which is 40, minus 39 for the think time, so that means r should be 1 second, and this is what we get. And likewise, if we now do the same model for n is equal to 4000 users with z is equal to 39, then r should be 4000 times 20 milliseconds, which is 80 minus 39, so that is 41 seconds. And that is exactly what we are getting in the test. Therefore, this model shows that when we have hit the bottleneck of Dmax as 20 milliseconds, the throughput is not going to increase beyond 48, but more importantly, it is but natural to have this 40-fold jump when we go from n is equal to 2000 to n is equal to 4000, because remember, response time is not going to be linear in just a number of users. So this jump of 40 times is but expected, and no matter what you tune, there is no way you're going to improve the performance unless you attack this factor of Dmax and try to reduce it from 20 milliseconds to much lower. Now, before we get into that, we should first figure out that where is this bottleneck occurring? What is causing this Dmax of 20 milliseconds? So that led to our next part. I mean, all of this was done in a matter of half an hour or so, but then the main part went in searching for the bottleneck. Now, fortunately for us, in the Oracle database that we're using, there were nice reports called StatSpec reports. And the usual suspect in a StatSpec report is to find out if there is any particular SQL that is hogging up a lot of time, or there are a lot of executions of SQL that the total time consumption is very high for the SQL processing. So this is for a 30-minute StatSpec report for the 4000 user test. If you look at this report, I'll circle the key parts. That what we are finding is that there is a high amount of logical physical reads for a particular SQL that has 87,688 executions, and this is taking up almost 46% of the total SQL execution time, whether you do it by number of reads or you do it by number of gets. So essentially we said, let's analyze this SQL further. Now if we further analyze it and we say that the total CPU time that's given is 2778, and total elapsed time for this SQL is given as 20,102.85 seconds. So this total elapsed time of 20,000, you divide by the number of executions, which is 87,000, and you will see that the average response time per execution is 0.23 seconds. Now that's not a whole lot, given that we are looking for a total response time of 40 seconds. So if we say that, okay, we look at your total executions per second, we have 87,688 for a 30-minute StatSpec report, that is 1800 seconds. So your total executions per second of this SQL happens to be 48. Now 48 is nothing but our bottleneck throughput or the business transactions per second. So which means that this particular SQL, which is our bottleneck SQL, is being executed 48 times a second. In other words, it is just once per business transaction. So essentially, the contribution of SQL processing to the business transaction time is not much, because this SQL takes up just 0.23 seconds of response time, and it accounts for 46.8% of all the SQLs. Therefore, no matter what you do, you are not going to have more than 0.5 seconds of SQL execution time per business transaction, and therefore the SQL execution time is not really a bottleneck at all. Although it appears to be high, and from what we've seen, we actually should normalize it per business transaction. So then we said, let's look at the top events in the database StatSpec report. Now that is provided by Oracle, and it clearly shows that the top event is something called the latch free event, which is taking up 98.96 or close to 99% of the time. Now this is because of excessive latch contention. We'll explain in a minute what do we mean by latch contention. So what is a latch in Oracle? Well, a latch is actually nothing but a very lightweight lock that will coordinate access to the shared data structure that Oracle maintains. So this is used to prevent the structures from corruption when multiple processes try to access the lock. So the idea is that whenever a session tries to access a latch, I mean, for example, you have to parse an SQL, then the latch is applied to it. So you try to get the latch as exclusive access. If you cannot get the latch, then you will spin on the latch, and then after a certain number of spins, you will get into latch sleep, and then you wake up and retry for the latch. So these latches are commonly used during SQL parsing. Now, how does SQL parsing work in a database like Oracle? That when you get an SQL statement, you first do a syntax check on it. The syntax check means that you will check for the syntax. For example, if you have a select from and here the select is misspelled, then the syntax checks will show that the statement is not correctly formed. If the statement is correctly formed, then the next step is a semantic check. And for example, if you try to select data from a non-existing table, it will fail at the semantic check. Now, if both these checks are successful, then you will check whether the statement exists in the shared pool. Now, shared pool will comprise of various SQL statements that are already parsed. So, essentially, the full string of the statement is taken and it is hashed to get a hash value. This hash value is checked whether it exists in the shared pool. And if it is there in the shared pool, it is what constitutes a soft parse, because you are hitting the library cache of this SQL statement, and then you grab the data from there and then you execute it. On the other hand, if it is not there in the shared pool, then you have a miss, and that means the SQL statement doesn't exist in the cache, and therefore you have to regenerate the SQL execution plan and find out which is the best execution plan to get the final query plan. So this is what's called a hard parse, and you have a latch is actually held for both a soft parse and a hard parse, because at the time you're hashing, you have to make sure that you are getting exclusive access on the shared resources. Now, when we look back at these wait events, so when we look at the latch free, and we did a further analysis from the Oracle StatsPack data, we could see that the average wait time per latch is 2330 milliseconds or 2.3 seconds. And for every database transaction, we have 5.2 latch waits. Now, what does this mean? Relatively, when we compared with the 2000 user test, I mean, we did not have 99% latch wait time, we only had 8.31%, and the average wait time was 2 milliseconds as opposed to 2.3 seconds. So we got almost a 1000-fold increase in the average wait time per latch. So how do we account for this? I mean, essentially you have to convert it into accounting, that how does the latch wait time contribute to the overall business transaction time of about 40.5 seconds that we saw in the load test. So the total wait time per business transaction for latches would be equal to the number of waits per business transaction times the average time per wait. Now we can go further by looking at the number of waits per business transaction as the number of waits per database transaction multiplied with number of database transactions per business transaction, and then we multiply by the average time per wait. And we have data in front of us. So if you look at the number of waits per database transaction, it is 5.2 because that is provided to us by StatsPack. If we look at the average time per wait, that is 2.3 seconds, that also comes from StatsPack. But what we don't have in front of us is the number of database transactions per business transaction. Now to get that, we look at a different section in the StatsPack report, which is called a StatsPack load profile, which gives us all the per second rates of logical reads, hard parses, sorts, executes, and the final row is the number of database transactions per second, which is shown as 157.7. So that is provided to us by StatsPack. If you look at the number of business transactions per second, we know it is 48. Number of database transactions per second is 157.7. Therefore, the number of database transactions per business transaction is 157.7 divided by 48 or 3.29. And this is what we go back and plug in a previous formula. So this way we will get the total wait time per business transaction is 5.2, which is the average waits per database transaction, times 3.29, which is the average database transactions per business transaction, times 2.33, which is the average wait per database transaction. So this way we will get this multiplication of all three factors as 39.86 seconds. Now we actually look at this vis-a-vis the total breakdown of response time. So average response time for 4000 users was 40.5 seconds. We have proved through the StatSpec analysis that the latch wait time per business transaction was 39.9 seconds. We also estimated the SQL execution time per business transaction as 0.5 seconds, and the rest is miscellaneous of 0.1 seconds. So it's very clear that the main culprit out of all this response time is not the SQL execution time, it is actually the latch wait time. Now once we've proved this, that we have to attack the latch wait time, then we need to see what do we need to do about it. So we saw that the SQL parses causes latching, and then what do we do about it? Well, we look at the StatSpec load profile and we see, well, there are total number of parses and total number of hard parses. The total number of hard parses, remember, hard parse is that which has a library cache miss and it goes about regenerating the execution plans, and that is 0. That means this statement is already there and we have nothing but soft parses, which is about 14,000 per second. Now if you look at large databases worldwide, it is common to have 100 to 1000 parses per second, but here we have a humongous amount which is more than 10,000 parses per second, and that is clearly causing a problem. So we need to figure out more that what is causing this parsing, and we need to decipher what's going on. So first we tried some tuning, given that we have some latches. I mean, remember, all this is happening in real time within the day. So we tried increasing spin count, tried increasing the cache cursors, we tried to force cursor sharing, increase SCH area, increase buffer. A lot of stuff we tried, but it was to no avail. And finally we said, well, let's try to get to the root of it. So when we try to get to the root of it, there is a section of the StatSpec report which talks about parse calls. Now we saw that 54.89 and 11.29, I mean almost close to 66% of the parses were occurring in two functions which are labeled as GF global policy and GF master policy, and these functions were causing all the problems with respect to the latching. Now what are these functions? What is the contribution to the overall CPU time? What are they really a bottleneck? So let's analyze it further. At least we know that these are the two functions which we really need to analyze further. So if you look at Oracle also gives you a TK prof where you can actually analyze the Oracle trace for statements and figure out, what is the parse, execution and fetch counts, what is the CPU time per call. So we looked at these two functions on the Oracle TK prof tool, and we saw that the first function had a count of 207 parse count, and for a given trace of a business transaction, and the second one had a count of 40 for the trace of the business transaction. And if we look at the total CPU time spent across these two just in the parsing, we see that these are called a total of 247 times, but they have a total CPU time of 0.02 seconds. And if we look at our total demand, the bottleneck also had a total demand of 20 milliseconds or 0.02 seconds. So now we will get on to the next section of the last video in the series to be able to figure out where are these policy functions coming from. Do we have control on changing it? It could be part of the code, it could be some attachment. Do we have any control over it? And if you don't have any control over it, then with all the analysis we have done so far to figure out this bottleneck Dmax, what do we do in the amount of time that is left, given that the auditor is going to come tomorrow? So let's move on to the next video in the series.